Hi, welcome back. We're up to lecture 14 now, and a new topic, analysis of variance. And what you'll see is we've been doing analysis of variance in multiple regression, but in fact we've been doing really difficult types of analysis of variance in multiple regression. So if you've made it this far, you've made it over the hump. You've made it past what I consider the most difficult topics, mediation and moderation in multiple regression. So hopefully you'll see that this new topic, analysis of variance, is just a simpler case of multiple regression. So take it easy this week. It's a new topic, but a lot of the old concepts that you've already learned will reveal themselves again. So in this lecture, there will be 3 segments. At the beginning, I'd like to talk about this general linear model that encompasses multiple regression and analysis of variance. And what you'll see is analysis of variance is just a special case of multiple regression. It's sort of an easier case of multiple regression because the predictors are not correlated with one another. And they're not correlated with one another by design. In the second segment, we'll do an introduction to ANOVA. It's just a one-way between groups analysis of variance is a good place to start. And then in the third segment, we'll do a little bit more challenging design, a factorial ANOVA. But first, let's talk about the GLM. GLM, or General Linear Model, is just a mathematical framework that's common to a lot of statistical procedures and is the bridge between last week and this week with respect to this course. So everything that we're doing in multiple regression and everything that we're doing this week going forward with analysis of variance, they're all just instances of GLM. So the general linear model encompasses multiple regression and ANOVA. And as I said, ANOVA is just a special case where the predictors are orthogonal. The 2 main characteristics of the GLM are that the relationship between the predictors and the outcomes, or in experimental design and ANOVA, I might use independent variable, dependent variable instead of predictor outcome. Those relationships are linear and additive. So we've tested those assumptions, particularly the linear assumption in multiple regression. We're going to have a lot more to say now about this assumption that they're additive. That's the characteristic of the GLM, but that doesn't mean we can't test for non-additive effects. That is, over-additive, under-additive, in other terms, interactions. We did that when we tested for moderation in the last lecture. By faking out the GLM, so to speak, what we did is we added in a product term. We took the product of a predictor and a moderator variable. So in lecture 12, the example was looking at the product of extroversion and socioeconomic status. We created a new variable that was the product of those 2 individual variables. The GLM, the R software, it didn't know that. It didn't know that we created a product term and put it in there. So it didn't know it was actually testing non-additive or interactive or moderating effects. So we can do that. We can also test for nonlinear relations by transforming variables. So that's the sort of cast that the GLM has, is linear and additive, but we can fake it out and put other things in there to test for nonlinear or non-additive effects. So where we started out with simple regression, that's a simple example of a general linear model. It's linear and it's additive. So remember, we were testing the assumption that the relationship between x and y is linear. We tested that assumption by plotting a scatter plot and looking to see if there's a linear function, checking for homoscedasticity. The additive part has been there all along. We haven't really stressed it, but it's just each time we add in new predictors, we're literally adding new predictors. We're not multiplying, right? Again, we can trick the GLM by adding a product, but we have to add the product. We can't just simply multiply in the regression equation because that's not the framework of the GLM. So there's the simple regression. Back to one of the old examples in regression, we could predict faculty salary with years since PhD. We could do multiple regression, where we predict faculty salary years since PhD, number of publications, and then, as I keep alluding to here, we could trick the GLM and throw in a product term, so I could test for moderation there. We didn't actually do that with that example, but we could. Again, it's my prediction. I haven't done it with those data, but we could do it. I predict that number of publications is probably more important early on in a career than later, and we could test that with the product term by doing a moderation analysis. Those two designs, that simple regression and that multiple regression, are exactly like a one-way ANOVA and a factorial ANOVA. It's just that when we do ANOVAs, we're going to be dealing with predictors that are categorical. So in a lot of the examples that we did with multiple regression, the predictor variables were continuous and the outcome variables were continuous. So predicting faculty salary from number of publications. Both of those variables were measured on continuous scales, and we had a range of values in our distributions, in our sample. Here, when we do analysis of variance, we're dealing with experimental designs. So go back all the way to the first week and the idea of randomized controlled experiments. Analysis of variance is typically employed just for those special cases where we have random assignment to conditions. So our predictors are now, they're no longer continuous variables like number of publications, they're conditions in an experiment. So they're discrete categories. That makes life a lot easier mathematically. You'll see that as we go through a one-way ANOVA in the next segment. But it's represented, I like to use the phrase under the hood in R as an analogy to how an engine works in a car, right? Under the hood, R works off of this mathematical framework, the general linear model. It doesn't really matter that it's an ANOVA versus a multiple regression. It's all mathematically the same thing. But to us, inputting stuff into R, it's easier to think about this as an ANOVA because it's a simpler design. It's a cleaner design, and that's why, as an experimental psychologist, that's my training as an experimental psychology, I really like the ANOVA procedure. It's very clean and very easy to interpret the results. So here we could do a one-way ANOVA where I'm predicting faculty salary, but I could use a categorical predictor rather than a continuous predictor. So that's why I put gender in there. Again, go all the way back to week 1. That's not the greatest independent variable, right? Because it's a quasi-independent variable. I can't manipulate or randomly assign faculty to be male or female. That's just a variable that they come to the experiment or study with. A factorial ANOVA is just looking at the combination of categorical or discrete predictors. So the example, I'm sticking with the faculty salary. We could do gender and race. Again, they're categorical, and then we could put in their interaction. And that's the flavor of an experimental, factorial experimental design. Again, a better experiment, if we want to get at causal mechanisms, is doing random assignment to conditions. But obviously, in this case, we can't do that. So I've already said this, but just to be clear, we typically employ ANOVA for randomized controlled experiments. Again, discrete categories as predictors, and then still looking at a continuous dependent variable. If we only have 2 conditions, so again, go back to the first week of the semester, or the first week of this course, and we talked about the polio vaccine studies. Children were randomly assigned to either get the vaccine or a placebo. So there were just 2 levels of the independent variable in that experiment. So there you could just do a t-test. So if there are 2 distinct groups, that's an independent t-test. If there are 2 paired groups, or the same people in 2 different conditions, that's a dependent t-test. What ANOVA allows us to do is compare as many conditions or as many groups as we want. So we could have multiple groups or multiple conditions. If they're independent groups, so separate groups of subjects in each condition in the experimental design, then that's a between groups ANOVA. If they're the same subjects measured repeatedly, like over time, then we'll use a repeated measures ANOVA. So this is analogous to the independent t-test and the dependent t-test. And we can also do null hypothesis significance testing with analysis of variance. It's just rather than getting a t statistic out of the results, we'll get an F ratio. And in the next segment, we'll talk in great detail about what the F ratio is. For now, you can think about it as just systematic variance relative to unsystematic variance. Again, it's just like any other NHST. It's a ratio of sort of what we observe in our experiment relative to what we would expect just due to chance. So it's systematic variance. It's variance we see across our groups, across our conditions that we can attribute to our manipulations relative to just how much variance there is not relative to our conditions, just sort of unsystematic, just due to chance. Like the t-test, the F ratio or the F test has a family of distributions. In the t distributions, there is a family of t distributions, and we could get p-values associated with t-values depending on degrees of freedom. Same thing with the F test. There's a family of F distributions, and which one of those distributions to use depends on the number of subjects, just like in a t-test, but also the number of groups. So I can represent that. This was actually code or a graph that's created by code in R. So this is R output, just looking at Fisher's F ratio, and these are the sampling distributions of the F ratio based on different degrees of freedom for the number of subjects and the number of groups. So it's not really important to know, the difference between each of these, but what you see generally is an F distribution, something like that. This is analogous to the t distribution. Remember, the t distribution or the z distribution was just a normal curve, right, where the extreme outcomes were out here at the ends in the tails. So if we wound up way out in the tail in the t or z distribution, we would reject the null hypothesis. We don't have tails like that in the F distribution, and it's not symmetrical like that in the F distribution because the F ratio is a ratio of variances. So it can't be negative. Variances can't be negative. The lowest it can be is 0. And if the expected value under the null hypothesis is just 1 because it's systematic to unsystematic variance. If there is no systematic variance, that's the null hypothesis, then the F ratio should be 1. And you see that's right here in these distributions. So you'll see that that's right in the center point of the distribution. So if we get F ratios, you'll see here's 2.0. If we get F ratios up around 3, 4, beyond that, then we're way out here in the tail of the F distribution, and that means we'll reject the null hypothesis. We'll claim that there's a significant effect happening in our experiment. But I'm getting ahead of myself a little bit. That conceptual piece will come through as we do examples in the next segment. For now, I just want to wrap up the general linear model and introduction to ANOVA. Just remember that this general linear model is a mathematical framework that encompasses both multiple regression and analysis of variance. And to be clear, analysis of variance is just a special case of multiple regression. It's a case of multiple regression where the predictors are not correlated. I'll use the phrase orthogonal for that. Okay, so ANOVA is multiple regression where the predictors are orthogonal. And what's new is just the F test and that we're dealing with experimental designs. It's a lot cleaner. It's a lot easier to interpret the output. So as I said, if you've made it this far, you've made it past the worst part of the course. This stuff is really, really clean, simple, and I think pretty elegant. So thanks for sticking with it.